All right. Yeah, thanks everyone. My name is Giovanni Campagna. I'm a PhD student at Stanford, and I was formerly GNOME developer, GNOME Foundation member. And today I'm going to talk to you about some of the work we're doing at Stanford on building an open source, privacy-preserving, programmable virtual assistant. And fun fact, even though I was a GNOME developer before, this is my first time giving a full-length talk at GWADEC. So thank you very much for giving me the chance to present this work. And we're interested in virtual assistant because we see a great opportunity in what we call the linguistic web. The idea that the natural language will be the uniform interface that go beyond the current PC-based mouse and mouse, keyboard, and touch. And virtual assistant will subsume websites, search engines, and mobile apps in a vision because they're able to see all our personal information, intermediate all the digital services that we access, and help us choose among competing offers. But virtual assistants also present a risk, because what we are observing, especially in the United States, is that there is a proprietary linguistic web in the making. Alexa has 70% of the 76 million installed base of smart speakers in the United States. It already supports 60,000 compatible IoT devices and more than 100,000 third-party skills. And the rest, the remaining 30%, it is mostly Google Home, Google Assistant, with the scraps for HomePod and Bixby. And this is going to create a powerful oligopoly between the two dominant players, Alexa and Google. And in GNOME, we are used to monopolies. Windows has 90-something% of install base, but this is worse because a virtual assistant has also access to massive amounts of personal data and presents a real privacy risk to allow this proprietary monopoly to exist. And so why is this happening? Well, the thing is that virtual assistants are unlike other applications. Natural language technology, the technology to understand the natural language sentences from the users, has a very high barrier to entry. You can either make it unusably brittle using old school technology like regular expressions, scripted dialog trees, the kind that you would have in like a call center phone applications. Or if you use the state-of-the-art technology, that requires millions of dialogues collected from users, annotated by contractors, each one of them with a formal representations. This is not only very, very expensive. As you can see, Amazon has over 10,000 of these employees continuously collecting and annotating sentences. It's also terrible for privacy because everything you say has to be collected and listened by these large companies. And so what we're observing is only the largest companies can afford to build virtual assistants. Does it mean that community and open source have no hope to compete? Well, yes, unless we change the technology. And that's what we are proposing to do today. And so in the rest of my talk, I will first present a new, finally cost-effective way to build virtual assistants that reduces the need to have 10,000 employees. This new methodology is based on formal languages that define the capabilities of the assistant precisely. It uses a neural network model to bridge the statistical nature of natural language, the imprecise statistical nature, to the formal capabilities of what the assistant can do. And we're going to present a way to use data engineering to synthesize large data sets instead of annotating each dialogue by hand. I will then present how we can preserve privacy, autonomy, and provide convenience to the user. I will show a federated architecture for a virtual assistant, and I'll show how our virtual assistant supports a new class of commands we call compound commands that no other virtual assistant have. I will then talk about more specifically how the virtual assistants can exist on the desktop on a traditional PC and what integration opportunity exists between a voice assistant and GNOME. And finally, I will talk about where we are and where we're going with our project. And so the first part is, how do we lower the barrier of building this conversational AI technology? Well, we are engineers, and And as engineers, we frame the problems along metrics that we can evaluate. In particular, we see this barrier to entry having 5 more important metrics. First of all is cost. There is many possible dialogues that the user and the virtual assistant might take, and we need to support all of them. There is a life cycle problem. There is a cold start. We have nothing. We are adding a new capability. We don't have data. How do we get there? And once we have data, once we have users, how do we refine iteratively? There is a usability problem, like what coverage, accuracy, and robustness can our assistant achieve? And do we actually get to the point where the users can achieve their tasks successfully? There is an effectiveness, like in terms of how precise and how controllable the assistant is. If it is entirely statistical and user-driven, there is a risk that it escapes the control of the developer, end up like a certain famous Twitter bot by Microsoft a few years back that didn't go very well. And finally, there is a matter of scalability. There is 1.8 billion web pages out there. There are thousands of natural language that people speak across the world. How do we expect to have enough resources to support them? Well, to address all these metrics, it is clear that the current technology is insufficient. We need a better engineering methodology that is focused around these metrics. And what we call the clues methodology that we approach is to build tools that let the world build assistant, eliminating both the requirement for people, for human resources, as well as the requirement for data. And our approach is grounded on a semantic parser. A semantic parser is basically a compiler for natural language. It takes natural language input and it translates it, in this case, to a high-level virtual assistant programming language. And we propose to have a common virtual assistant programming language we call ThinkDoc that we designed. It is essentially a DSL that optimized for what a virtual assistant can do. And we hope that all assistants will be built around this language so we can share the tooling and the work to build the assistant. So how do we use semantic parsing to support a virtual assistant? Well, let's say the user is starting by saying, okay, I'm looking for an Italian restaurant. The sentence is passed to the semantic parser. The semantic parser will then translate that sentence to a ThinkDoc statement, a ThinkDoc query, that will look up in the restaurant database of Yelp, and will look up in particular for rows where the food is Italian. And this ThinkDoc statement is passed to a ThinkDoc runtime, a standard just-in-time interpreter that is going to execute this statement, return the results. In this case, it finds Terun, that is, in fact, the best Italian pizza restaurant in Palo Alto. And this result is now passed to the general dialog state machine that supports all the skills and all the services. And this state machine will take the results and produce the response that we can show to the user, both at a high level in terms of what action the agent is taking. In this case, the agent is taking the action to proposing one result, and in terms of the natural language we show to the user, I have found Terun, would you like a reservation? And note in particular that the high-level state that the state machine has produced is passed back to the semantic parser. It now becomes an input that can be used to understand the next utterance from the user. And this is where a semantic parser differs from existing intent-based systems, because we don't need to model all the different intents, all the subsequent turns. The state is encoded, and the neural network will understand how to interpret subsequent sentences. And so how do we use a neural network to build a semantic parser? Well, at the very high level, a neural network is essentially a magic black box. It is a differentiable function that is trained from examples, from input and output examples. And in principle, it can do anything. In fact, there is quite a bit of empirical evidence that it can do the neural networks can solve any problem if you have enough training data, if you have enough pairs of input and output examples. And In particular, we are leveraging the BERT network from Google. That is an open source neural network that has been trained to learn just natural language, not English or other natural languages, from just by scraping all the web and understanding how sentences fit together. And then we fine-tune this network for the semantic parser. And now in semantic parser, the data is the utterance, what the user has just said, the state of the agent, what the agent just took at a high level formal representation, what the agent just said in the previous state, in the previous sentence, and the program, what we expect the neural network to produce, that is, what is the next query we want to execute or the next action we want our system to execute. And so we said neural networks can learn from data and can learn anything provided we have data, but we need millions of examples. We are back to this problem of how do we collect this data without annotating. Well, we propose that instead of specifying the virtual assistant and the dialogue agent in terms of actual just manually built data sets and manually annotated data sets, one should provide a higher level specification. We would like our specification to be the schema. I provide you the database, the list of columns, the types, and a few annotations on each column indicating how that column is referred to in natural language. We provide this schema to our tool, which we call Genie. Genie is the core component of the Almond virtual assistant that takes care of the natural language understanding part. And Genie comes with a general state machine that covers all the dialogues, or at least all the dialogues where the user is trying to perform something, all the dialogue where the user is trying to get the agent to do something. And what Genie will do will automatically generate all the possible dialogues, or a large samples of all the possible dialogues that fit into this state machine and talk about this new database. And so this is one example when it's now talking about restaurants, and it's talking about a user is looking for information about a food place, is looking to book it, and now the agent responds with a proposal, and the user can then follow up, change their mind, add information, and so on. So how do we automatically convert the high-level specification of the database into natural language dialogues that we can use to train our semantic parser? Well, we observe that there is a natural mapping between database operations and natural language, at least in the form of templates. So, for example, the database operation of selection or filtering maps to specifying a table that have a parameter equal to a certain value, or for example, restaurants with rating equal to 3. Projection corresponds to extracting one field of a table. Aggregation, we can express it as the number of entries in a table, or so the number of restaurants, and so on. And so for every operation in a database language, in our ThinkDoc database language, we can write a set of templates that express how that database operation is reflected, and use those templates to generate data to train. But of course, natural language doesn't fit the templates. If it did, then we could use the templates directly to understand the user, rather than going through this convoluted process of generating data, training a neural network, and then using the neural network. In fact, natural language has a lot of variety, and our approach is to capture as much of the variety as we can in a domain-independent manner. So, for example, we leverage grammar. We leverage the intrinsic grammar of English, so we can capture the different purposes of the sentence, and we can say not only search for restaurants, but also what are restaurants around that serve Italian food, or I'm looking for a restaurant. These are all the different types of sentences. We can also leverage the certain standard types, such as people, objects, time, and location, and the way those map to different WH words in English. And furthermore, we have a fine-grained type systems that covers weight, height, age, and so on, all the standard measurement type. And for each of those, we can immediately identify the standard words that one would use in English to refer to those properties, and then apply them to all database that uses those types. And it is not enough, though, to capture the variety in a domain-independent way. We also need to capture the specificity of each database. And as I said, we do so by having annotations on every field. And in particular, we noted that every field can be used in different ways in a sentence that correspond to different parts of speech. So, for example, if we look at the alumni say, a hypothetical LinkedIn-style database of people, we can say that we can ask for who has a Stanford degree, or who studied at Stanford. That is a different part of speech. Degree is a noun and studied is a verb. Or we can say who was educated at Stanford. Now educated is a passive verb. Or we can say who are from Stanford, and that's a preposition. Also note that for some fields, we have access to all the different parts of speech. They're all meaningful. For some, like cuisine, we can ask which has Italian food, but we cannot ask which is Italian food. There isn't really anything, but there is such a thing as which is an Italian restaurant. That's where Italian alone is an adjective that modifies the cuisine. And so having specified our database, how do we go and having the ability to query our database in natural language, how do we go and make dialogues that last more than one turn and not just search in our database? Well, we observed that there is a high-level structure that applies to all dialogues that where the user is trying to perform a transaction, trying to perform some action on the virtual assistant. So let's take this example. This is taken from the Multi-Wizard of Oz dataset. It's a standard benchmark that was released from the University of Cambridge a few years back. And it is about restaurants in Cambridge, UK. And so the user is looking for a restaurant. First, they're going to search. And there's going to be a little bit of back and forth between the user and the agent, as the agent proposes some results from the search and the user refines the search in different ways. At a certain point, the user is going to pick one restaurant they're interested in, and now they're going to move on to completing the action, and the agent is going to require, in technical terms, log fill all the missing information to perform the action, such as the number of people in the reservation or the time. And finally, once the agent has all the information, it can go ahead and perform the reservation for the user and show the result, in this case, the confirmation code to the user, and thank them and move on. And so our approach is to capture this general structure shared by all transaction dialogues in an abstract state machine that is independent of the specific virtual assistant skill, the specific domain. And this state machine connects dialogue acts, such as a search request, the dialogue act from a user in orange, and agent dialogue acts, such as proposing one result or proposing multiple results from an agent in green. And note in particular that there is an exponential number of paths that one can follow along this state machine from the initial state to the end state. And so even though this state machine is relatively small, it has about 20 dialogue acts, we can already see that we can generate many thousands of possible dialogues that we can use to train. And we can also see that if we were to understand all the different possible dialogues from data that we collected by writing those dialogues by hand, we will need millions of dialogues. We will need really Amazon scale to understand the state machine. But because we have encoded the state machine in an engineering way, we don't need to write all these dialogues individually. And so zooming in, our state machine, as I said, is domain independent. And it does so by again representing every dialogue act that the user and the agent perform in terms of templates, which are essentially sentences or families of sentences with placeholders. And so the result that comes in of the ThinkTalk runtime is translated by the state machine into an abstract state, into one of a finite number of categories, in this case, a small result. From there, the agent can decide to propose one or propose multiple results. If the agent proposes multiple results, then the user can ask a question on one to decide which one to go for. Or it can just say, I don't like any of those. Do you have something else? Or if the user is accepting the result proposed by the user, okay, I can say, I like that. Can you help me, for example, book it? And so this is what happens when you put it all together. Given a small result, where in this case, the user was looking for a moderately priced restaurant in Palo Alto, and I found Terun and Coconuts, very nice restaurants around here. The agent can propose, I have Terun, it's a moderately priced restaurant that serves pizza, or I have Terun and Coconuts, and both are moderately priced. And then if the agent proposed one, then the user can ask for an action, in which case the agent is then gonna go on and say, okay, for what date would you like your reservation for? And so to recap this part, our new technological approach is a high-level specification at the domain of interest in terms of a database schemas or the APIs. So the database schema in the example was the restaurant schema, and the APIs was a booking API. And a few natural language, about 6, 12, 15, around that number for every field. And we can combine that with a general state machine and generate many thousands of possible dialogues automatically. It's just a compute cost. It's basically running a very, very slow compiler. And then we can use to train a state-of-the-art neural semantic parser that understands not only what we had in the templates and in the state machine, but can generalize to transitions and sentences that are not seen in our training data. And so we can actually be robust to things we didn't even think of, because first of all, we start with a neural networks that's just trained on natural language from the web. And second, we have a neural network that's able to generalize, and so we don't have to cover all possible paths. And that's why this approach gives us the best of both worlds. It is as easy to build as the old regular expression-based system or intent classifier, like classical intent classifier systems. But it is robust and generalizable as the data-intensive neural network that the proprietary virtual assistant will use. And that's why we believe that our approach is a unique opportunity, not just to match the proprietary assistants, but to surpass it, because no other assistant at the moment, before the proprietary assistant catch up, has the technology. And that applies to both the proprietary assistant now having the technology, as well as the other open source assistants. And so that was about how we make our technology, build our conversational AI at a much cheaper cost. Now that we have the technology, can we use it to build something more powerful and more interesting and more useful for users? And we start by observing that today's virtual assistants are a lot like browsers. You can navigate to all these skills, to all these 100,000 skills in Alexa, and we can interact with one skill at a time. But humans are not just browsers. They want to share information. They want to connect across different sites, across different skills. They want to aggregate information across different sites. And ideally, they would even let the assistant decide in certain situations where it's safe for the assistant to decide automatically without the human being involved all the time. And so let's look at one example. Bob is one of the 8% of America that has a respiratory disease. And no, it's not the coronavirus, because this slide is old. Bob has asthma, and he would love his assistant to help me. And so he can ask the assistant to help us with his device. So when he's using his inhaler, he should record his GPS location, for example, in his Box account. Bob's doctor, Dr. Smith, will want to be alerted, and in a customized, personalized way about Bob. So he will want to be alerted if Bob's peak flow is less than 100 liters per minute. Bob can also use his assistant to share his location with his dad. For example, if Bob ends up in the hospital and is incapacitated, the assistant can automatically alert his family. And also Bob can use his assistant to decide, based on instruction from Dr. Smith, if Bob is running and the air quality index is above 500, it is unsafe. Bob can be alerted, and the virtual assistant can decide that it is time to alert Bob. So how do we support all these capabilities in natural language? Well, we observe that natural language is inherently compositional. This is just a property of how natural language works, that complex sentences, complex commands are built from basic primitives. And here are some examples of the primitives we're talking about. There is what is the favorite command of PhD students is when my advisor is online on Slack, send me to away. We have commands that connect multiple skills, such as automatically uploading all my Instagram pictures to Twitter, so I don't have to upload them twice. We have commands that require computation, such as what is total size of all the files in my Dropbox, or all the files in my Dropbox that have a certain name or a certain folder. And finally, we have commands for access control. So, for example, I can share my security camera with my parents, but only when I'm not home. So they can help me with taking care of my house and ensuring I'm safe, but also don't spy on me. And so, again, as you probably have guessed, the way we are going to implement this is by translating every utterance into a formal representation in a ThinkTalk programming language. And so we extend ThinkTalk now, instead of having just a database query or a single action, we have a control construct, which we call when, get, do, that combines up to 3 primitives, up to an event, a query, and an action. So, and you can see that all the commands I've shown, it can be represented in terms of this when, get, do construct, making it a very powerful construct that supports many hundreds of thousands of very useful commands. And the primitives are taken out of Thingpedia. Thingpedia is an encyclopedia of things that we have collected. You can think of basically a very large version of GNOME online accounts that has all sorts of services. And it currently has supports for 129 skills and 272 functions. And for every functions, we classify it in whether it's a query, like a database style query, or it is an action. And for everyone, we have natural language information associated so that we can use our Genie technology to generate the training sets to understand all these commands. And Thingpedia allows us to have a privacy-preserving architecture for Almond, because we can separate what is the public knowledge of the virtual assistant, the interface, the code. It is basically a repository of public knowledge, and it lives in, you can see this little cloud, from what is private. So the assistant is now running on my own personal device, is now running on my own PC or my own phone. And now only the assistant has access to my personal account. It downloads the code and the information from Thingpedia on demand and execute the commands privately. And the missing bit now in architecture is sharing. Sharing means accessing data that is not only owned by my virtual assistant, but is possibly owned by other people, because, as we said, sharing is an important key of what we will want our assistant to support. And we start by observing that virtual assistants serve requests on the user's behalf. And so we can, if my virtual assistant can serve requests on my behalf, it can also serve requests on behalf of other people with permission. And so we have a federated architecture in which different virtual assistants communicate to share data with each other. And this provides an architecture without any third party, without leaking any data. It is generable because any service can be controlled. If you can control it for yourself, you can control it with, you can share it with other people. It is usable because it is backed by natural language. And finally, it is private because there is never any access directly to the service. And so there is no risk that more than the access that is actually granted is provided. And I don't have time to go into details for this part, but if you're interested, I recommend you look at our paper. And in the next part, I'm going to talk to you about what you're probably most excited about, given that it's a GNOME conference and we care about the desktop. It's missing the word assistant. How can we use a virtual assistant on a desktop computer? And the way I see it, there are three major use cases for a virtual assistant on the desktop. The first one is control. We can replace long menus and replace opaque terminals and very complicated bash one-liners with natural language that is a lot more accessible. And furthermore, we can control apps without switching, which improves focus and improves multitasking. There is search. We can access all our content on our computers and provide a uniform semantic interface that is a lot more fine-grained than the keyword-based search. And finally, as I've shown, we wish to support automation. Replacing bash scripts with natural language scripts, we're going to make them a lot more accessible to people who don't have the expertise or the time to learn bash, but they understand natural language and they can use this to automate it. And furthermore, with automation, we might be able to combine graphical user interfaces like traditional apps that are not virtual assistant enabled and combine them with virtual assistant commands and control them with voice. Going more detail in control, what we wish to do is to start by exposing existing capabilities to voice. And so here are some commands that our assistant supports on GNOME. You can lock your PC, you can take a screenshot, you can lower the volume, and so on. And the interesting thing is that there are natural entry points for all these commands in the terms of dbus interfaces. There are standard interfaces that some of them apply across all desktop environments and some are GNOME specific, but at least they are standard and well supported that allow different components to communicate, and one of them can be a virtual assistant. So we can use the GNOME interface for screenshots, for screen locking. We can use Pulse Audio. And we also have a shell extensions for all the interfaces that are missing. And another area where control can be useful, we don't have yet in our prototype, is Empress to control music, which is usually a standard capability for a system. It's a very important use case. The next one is search. And there is a lot of possible queries that are interesting in a desktop, like find me the spreadsheet I was editing last Monday, or what would be my favorite command on search is just pull up the right presentation. I don't want to go and hunt where did I put the right PDF for this. And of course, the natural integration for search is Tracker. It's somewhat unfortunate that the Tracker presentation of this Quadec is happening in parallel to this one at the same time. But Tracker provides a semantic database of all the content on the PC, and it provides a query language interface, Sparkle. And as I said, our Genie technology is able to take a database schema and translate it into a natural language interface. And so we should be able to do that for Tracker. We should be able to take think.code code and translate it into Sparkle query and then be able to semantically query all the content that is indexed by Tracker. We might be able to do the same for Evolution Data Server, for calendar, for emails. And note in particular that unfortunately we cannot directly leverage the existing search provider interface for the GNOME shell, because the information that is exposed by the search provider interface is not semantic enough to be able to compute and talk about it and build a dialogue in natural language. But so this, I think the virtual assistant is an opportunity to define basically a version 3 of the shell search provider interface that is now semantic and it's accessible for natural language. And finally, automation. Automation is about doing away with repetitive tasks and automating existing application. And I had a video here in the presentation. Unfortunately, because I had to upload as a PDF, I cannot show that. But we have a prototype that does automation on a browser using a browser extension and using Puppeteer to control pages. Puppeteer is like Google's version of a Selenium WebDriver, like standard API to control web pages automatically. But you can imagine you can use like other OS level primitives such as @spy from the accessibility tool stack to control any application and make it natural language enabled. And well, this is very rough work. At the moment is still a prototype, but it's an active area of research, and I think it's very interesting. And finally, to wrap up, where we are and where we're going next in our Almond project. Well, where we are is that we are a project of the Open Virtual Assistant Lab. That is a lab at Stanford. It's sponsored by the National Science Foundation, so it's paid by your American tax dollars, as well as the Alfred P. Sloan Foundation and the Stanford Human Centered AI. We have a lot of faculty, shown here some of them in a picture that was featured in the New York Times, as well as a lot of students. Here in the slide, I'm showing the current active PhD students, but we have a lot more master students and former PhD students that have graduated and left. And our current status is that we are at 1 point something. I think we are at 1.8. The current version is that we have a basic prototype. We have a web version that you can go and try at your own risk. It is a very rough, it is a research prototype. We have a version for GNOME, as I mentioned, and you can download it from FlatHub, as well as the moment you install it, GNOME is going to prompt you to install the right shell extension from the shell extension store to unlock the full capability of the assistant. We also have partnered with the Home Assistant. If you've heard of it, if you haven't heard of it, Home Assistant is this open source home automation smart speaker like IoT gateway solution. It's a very popular, very active community, and we are available as a Home Assistant add-on as well as an official integration of Home Assistant. So you can basically build an Almond, a Home Assistant enabled smart speaker with entirely open source component. And we also have an open developer program, so you can create a new skill for Thingpedia in a few minutes if you follow the tutorials. I mean, of course, if you're going to build something new, it might take a little longer. And currently, the repository, the API are free to use. We don't have any API limits. So we are very happy to collaborate. But as I said, we are at 1.0. We are building towards 2.0 because our current Almond is a very rough research prototype. It's really not very good. It is a research project, and it had to support the papers that we have written over the years. In fact, the currently deployed version of Almond has very limited dialog capabilities. And as we develop our technology and extended our Genie methodology, we increase the dialog capabilities. We are currently working to bring in the new dialog technology to Almond. And dialog is more complex than, for example, symbols, semantic queries, or single commands that you would issue to a traditional virtual assistant. So it's going to be hard to make it robust across all the 130 skills. We're going to focus first on the top 10 skills, the most important that we see empirically in virtual assistant, like music, weather, reminders, news, and so on. We also found that the Almond wake word is a little tough. There's a lot of different ways to pronounce the word Almond. Especially, I tend to stress the L, and the Native American speakers don't. And so we're going to rebrand with an easier wake word. But our goal is to provide an end-to-end experience, first of all, in the Home Assistant, as I said, and the do-it-yourself smart speaker. We will provide an end-to-end experience in Google and Alexa, so you can talk to Almond and experience our technology. And maybe, and why I'm here is that maybe GNOME can also be a first-class, first-supported platform for a new version of the Almond Assistant. And maybe we can have this kind of deep integration and deep kind of capabilities. And this is our tentative timeline.
So one quick reminder, we have 10 more minutes.
Right, I'm almost done. I have a few. Yeah, I only have a few more slides. So our timeline is that we started we started this road to Almond 2.0 in June 2020 as we got our new round of funding from the Sloan Foundation. We got $1 million from them, and we're very happy. And we are gonna this month or in the next couple weeks release a new development unstable version where we're gonna integrate the dialog state machine that I talked about in the first part of the talk. And we hope to have a developer beta that actually works to some extent around the end of the summer or the beginning of the fall quarter. And with the goal of having a fully supported third-party skill platform, as well as a fully supported, testable, early adopter-ready assistant by the first quarter next year. And we hope to be usable and ready for end users, not just early adopters, by the second quarter next year. And here I've highlighted some areas where we really love some community help. First of all, growing Thingpedia, adding all these new capabilities and making use of all these new APIs. Voice is another area where we would love some community help. On some platforms like Home Assistant or the browser or Alexa or Google, we get voice for free. On GNOME, we are implementing, we basically have our own voice code, and because voice is not an active area of research, we're just using off-the-shelf technology, and we are using proprietary Microsoft APIs for voice at the moment. Being able to, because our project started before Deep Speech and before Mozilla Voice was available, being able to make use of Mozilla Voice would be very nice. And finally, internationalization. Right now, all our research and our work have been done in English, but we would love to have help from the worldwide open source community to support all the different languages. And here I've listed all the community resources, and the talks and the links will be available after the fact. And at the end of the presentation, you can talk to me. And so to recap, I believe that we can beat, not just match, but beat the proprietary alternatives. I've shown how our technology, a state machine-based dialog agent, is more robust than traditional dialog trees, and it requires less work to support new domains and new skills. Synthesis is orders of magnitude cheaper than collecting and annotating thousands and millions of dialogues. End-user programming provides new capabilities that no other assistant has, like automation and access control, which is going to encourage the adoption with unique and usable features. And finally, we care about privacy, and there is an enthusiast users community that cares about autonomy and privacy, and we hope that we can leverage that to build the best virtual assistants. And of course, it's all free and open to all pull our contributions together. Thank you.
Thank you very much. We have time for questions, so do you want me to read them for you?
How many questions do we have? Because if we have an extra minute, I can maybe try and do a live demo and see how well it works.
Yes, we have 2 questions and 7 minutes.
Let me see if I am brave enough. I'm gonna select the entire screen. Okay, so as I said, we have a shell extension and we have our Almond virtual assistant. I'm gonna go into preferences and re-enable voice input. And so I can say, computer, tell me a joke. Here comes the joke. Computer, what time is it? And that's what it does. Yeah, so that's a very short demo, but you can see that there is an integration in the shell. It pops down, as well as the native GTK application that you can use on other desktop environments, or if you don't want to install a shell extension. Right, questions?
Awesome. So the first question is, how much work is it to add support for a different language?
So adding support for a different language at the moment is actually a lot of work, because as I hinted, our work is grammar inspired. Like we don't use the grammar at an understanding time, like to parse the user utterances, but we use it to generate. So you need someone who has a good knowledge of the state machine, of the think-talk language, as well as the grammar of the target language to build this state machine, these templates. But we are working to simplify that workflow. There is very mature natural language and machine translation technology to automatically translate from English to other languages. So we hope that at the moment, the work to enable other languages is substantial, but we hope to reduce the work considerably as our research and our technology matures. And that's also, I think one of the advantage of being so closely related to the research side. To Stanford, they are some of the best PhD students, and so that's an advantage. We get access to the technology.
Great. Next question is, any plans for UX work on the client app, the current GTK app?
That's another area where I would love community help. I have to admit that the GNOME client is something that exists because I love GNOME. It's it really is it's not something that we would have built unless it would have been me in a lot of ways, right? It's not assistants on the desktop like we have seen with Cortana. They're not very popular. But I love the GNOME community. I love the idea of having a virtual assistant in GNOME, and that's why I built it. But I'm not a UX person. I'm not, let alone a UI person, and that's why some help in improving the client application will help a lot.
Yeah, contributions, welcome them. I see two more questions. How does this compare to Mycroft, Mycroft.ai?
Mycroft or other assistants, like there's Mycroft, there's Firefox Voice. They're based on the classical technology of using intent-based systems. So at every point, your assistant has to decide the sentence I'm going to understand, it belongs to one of these like 5 or 10 different intents. And for every intent, I'm going to have, however many thousands of sentences that are manually annotated for that intent to get good quality. And of course, if you use a neural network, you need thousands of sentences. If you use a classical system, like an SVM or some other statistical method, you might get away with fewer sentences, but it will be a lot less robust. Like we might not understand, for example, synonyms. And so the problem of Mycroft or Firefox existing methods like other assistants is that they don't scale to the complexity of dialogues, and they require a lot of work to get the robustness there. They're not, the short answer, they're not state of the art, basically.
Great. And the last question is, what is current local overhead? RAM, CPU, network data?
It depends. So if you want to run the neural network locally, the neural network is about 500 megs in terms of disk footprint, and it's a pretty big network. It's 130 million parameters that you have to load in memory. So it's quite a bit heavy. You don't need a GPU to run the neural network in inference mode. We definitely need it to train it. You need a very big GPU to train. But that's why we don't expect at the moment to run the neural network, run all the parsing locally. We have spin up a server, and then so our current client will ship to our server, but our server still preserves privacy, because unless you consent to us recording, we don't record anything. We erase. There are no identifiers, there are no logs, nothing is collected unless you consent to collecting the anonymous sentences from what you type.
Great. So thank you very much, Giovanni Campagna.
Yeah, thank you for inviting, for offering me the ability to speak, and very happy to be here.